Hello, everyone. Welcome to my presentation. And today we are going to talk about the extending Linux kernel with Go and eBPF, which is an interesting technology. And this will be an overview to eBPF from Go perspective. Let me introduce myself. My name is Burak Tahtacı, and I'm working for Trendyol Tech as a software engineer. In most of my time, I'm doing security research and developing security software for 5 years. Okay. Here is the agenda today. First of all, we will talk about the Linux kernel and its behavior, and then we will talk about basically how the eBPF works and what are the main concepts of them. Also, we will cover some of Go libraries and SDKs for loading and running eBPF programs in kernel. And finally, we will do hands-on coding and seeing in real-life cases with Go and eBPF. Okay. Let's get started. I'd like to begin by the kernel itself. As you know that the kernel is the most privileged part of an operating system. It manages all the system resources, and the kernel is the center of the management for an operating system. So if you can introspect the kernel, we can get very detailed insights about our system. For this reason, kernel is the best place to implement observability, security, and networking applications as well. Because kernel has capabilities that can oversee all the events that are communicating with hardware and the other system resources. So, how we can extend our kernel through observability, networking, and security verticals? How to add new features or changing existing ones with relating with them? And what are the options? First of all, the kernel modules. Kernel modules, Linux supports the kernel modules, which are dynamically loadable programs into the kernel at runtime. It looks as a handy solution to add new features because you don't need to recompile the kernel or reboot them. However, there are some drawbacks for the kernel modules. Kernel modules does not support any mechanism to check the module is safe or not. So if there is a bug inside your kernel module, it may crash your kernel. So there is not any verification layer before the execution. In addition, the kernel modules depends on your kernel version. When your kernel version is changed, you might need to change your kernel modules code. The second option is changing the kernel source code and adding your awesome features inside the upstream Linux kernel code base. However, it might be pretty hard to get accepted for each change on your Linux kernel from the community. So the last one is really hard. So writing your own kernel may cost very, very huge. For example, the cost of writing Linux kernel from scratch may cost $1.5 billion. Yeah, there might be a good solution for this. So before we get started, we need to understand how the kernel works exactly. Linux kernel is event-driven. For example, all the components in the kernel are events. For example, system calls are events, hardware interrupts are events, or incoming or outgoing network packets are each of them is events. So kernel is also intermediary technology between the user-level processes and the hardware. So it abstracts the hardware from user and exposes drivers and programming interfaces. And each operation kernel can be treated as an event or interrupt. So the question is here, is there any way to hook these kernel functions for tracing or manipulating those events? So the answer is eBPF, which stands for Extended Berkeley Packet Filter. The classic BPF developed in 1992, and it was used to process network packets in an in-kernel virtual machine. BPF virtual machine was an execution environment for our BPF programs for packet filtering or packet manipulation purposes. It makes it easier to develop high-performance packet filtering applications in kernel. So BPF is very powerful. However, it's limited to packet processing domain. So the eBPF is the extended version of it. eBPF can hook many, many different points in addition to its networking capabilities. So it boosts the capability of visibility inside the Linux kernel. So we can basically define eBPF is a virtual machine that is running inside our kernel, and we can run our arbitrary user level codes in it. So let's look at the eBPF's technical perspective. Okay, there is a virtual machine inside the kernel. And this is a sandbox environment to execute our BPF programs. And we have a user-level driver application, which is developed in high-level language. And the driver program loads the kernel programs into the virtual machine. So many high-level languages, such as Go, C++, Rust, or LLVM, supports the SDKs and provides SDKs to develop user-level applications with eBPF. And the SDKs can provide a way to load kernel programs into the kernel VM. So actually, the eBPF kernel programs written in a restricted C language, which is different from the ANSI. Some of the features in C are excluded from this language in order to ensure that the kernel programs are safe to run in the kernel and it will not crash our kernel. For example, this restricted C language has not any loops, or no global variables, or no floating point operations, and so on. This language is not Turing complete. Okay, as you can see here, there is an example of eBPF kernel program, something like looks like this. This function attached to the execve system call and gets the commands which is executed, as you can see here, event.com. So this program basically listens for each execve system calls is triggered and extracts data from this event. Okay. To run this kernel code inside the kernel VM, we need to compile this them into the eBPF bytecode. So the Clang compiler utilized here, this translates this compiles the C code into the eBPF bytecode. So the compiled BPF codes look like this. This is the instruction set of eBPF virtual machine. This bytecode is now ready to install, to load inside the VM. And this eBPF VM only accepts something like that, this bytecode. And the SDKs can load these bytecodes into the VM directly. So just before loading to the VM, we must ensure that our code, our bytecode, needs to be safe to run in the kernel, because it will not crash the entire system, because if the kernel crashes, all the system crashes. And there is an architecture here that is called verifier. It basically checks our bytecode is safe to run in the kernel. So during execution, the verified bytecodes are translated into native CPU instructions, as we know, the push, pop, or something else, and that the virtual machine actually running on the hardware. So just-in-time compiler is the essential part of the eBPF's performance. So it translates each bytecode instruction into the CPU instructions on the fly. So it makes eBPF programs run fast as the natively compiled programs. So after the compilation stuff, our eBPF program is ready to hook the event. Okay, BPF was already developed to hook networking-related events, as we know. But eBPF can hook many points inside the kernel. For example, kprobes is one of them. The kprobes are the entry points of the kernel level functions, which can monitor the beginning of the events. So, and kret probes is the return points of the kernel level functions. eBPF can hook many other things like system calls or even user level functions to keep track of the user level processes with eBPF is possible. So these features makes eBPF is a high performance introspection tool for the Linux kernel. So we can get very detailed insights and metrics about the system through these system call hooks. Okay, the In order to develop the eBPF kernel programs, there are some helper functions inside the kernel, which is called the kernel helper functions. And it makes the development of eBPF kernel programs easier. So it contains some of the useful functions, for example, the random number generation, or getting system time, or printing messages, or accessing BPF maps, and so on. All these stuff are really useful while we are developing programs in kernel. Okay, another essential part in the eBPF world is maps, eBPF maps. Basically, the eBPF bytecodes are just executables. There is not any data inside of it. But sometimes your eBPF programs need to store its states, its metrics, or any kind of data. So maps are the solution here. Maps are the data storage and transmission system for eBPF. This is a two-way data communication channel between our user-level driver application and the kernel eBPF program. So we can enable to send data from kernel to user, or user to kernel level. Okay, the map supports very well-known data structures such as hash tables, LRU caches, or longest prefix matches, or stack traces, and so on. They are very useful to communicate each processes from kernel or user space. As you can see that the eBPF provides high-performance kernel tracing and observability options. So let's talk about some real-life use cases of eBPF, how we can use the eBPF actually in real world. Simply, main three categories could be covered with eBPF. The first one is observability. We can cover observability via event hooks. So eBPF can hook many points inside the kernel, and we can get inside and collect metrics, or access this state of each function call. And every point inside the kernel, eBPF can do the observability very well. And another case is about networking. So eBPF has strong abilities to work with network packets and manipulate them. Therefore, the high-performance traffic controlling and layer 4 load balancing applications could be developed via eBPF. And also, the eBPF can be utilized in some of security applications, such as intrusion detection systems, firewalls, or runtime security applications. So, all right, here's the thing, how we can write eBPF programs by using Go. And there are lots of ways to do it, but today I will cover two of them, which I've used before. The first of all, the Ebpf Go Library, which is developed by Cilium and Cloudflare. This is a pure Go library that mimics the libbpf capabilities. libbpf is the original BPF implementation that is in the upstream Linux kernel. So this library is very well documented and well tested. In addition, this library is the core technology behind the Cilium CNI. So it has a broad production use in networking and packet processing domains. The other project is GoBPF, which is developed as a part of IOVisor's BPF compiler collection project, which is called BCC. BCC provides lots of useful tools to load and run eBPF programs. It abstracts the logic behind the compilation and verification from the user. So it's easy to develop eBPF programs with BCC. So this library focuses on the tracing. So, but the BCC is originally developed for Python, and GoBPF is the Go wrapper for BCC. Okay. I wanted to mention about an interesting technology, which is called XDP. It stands for the Express Data Path, which is a part of the upstream Linux kernel, and it enables users to load packet processing programs into the kernel as early as possible layers, such as drivers or network interface cards. So packets can be processed before the kernel's TCP/IP stack does. So the eBPF programs can be loaded into many points before the actual Linux packet processing subsystem. So, for example, our XDP programs can be loaded onto the network hardware, which is called offloaded XDP, because all the packet filtering logic is offloaded onto the NIC besides the CPU. If our network card does not support the XDP can also inject our codes onto the network driver or early steps at the Linux networking stack. This makes the packet processing applications as early as possible, so the packet manipulation is extremely high performance when compared to the other traditional approaches. On the other hand, XDP sometimes referred as the kernel bypass technique because we can run code directly inside our hardware via bypassing our kernel. So it's similar to direct memory access in file operations. Okay, now it's the demo time. We will do a simple demo. We will look at some codes in action, which is a simple network intrusion prevention system. Here is the simple pseudocode or explanation how our demo works. We will first capture the network packets before the kernel does via XDP, and we will check the flags of the TCP packets that is incoming to our host. And if there is an Nmap Scan here, we will drop these packets to protect our host from the port scanners. All right. And then when we capture the port scan here, we will notify our user level driver program which attacker's IP, and we will pass through the eBPF maps onto the user level. If there is not fancy, we will pass the packet to the user level. All right, let's talk about some code. Here, there are simply two hosts here. This is the first one. This is my laptop here. We will behave as an attacker to our VM, and we will develop our code onto this VM. This is an Ubuntu server. And our XDP program consists of mainly two parts. The first one is the kernel program, which is xdp.bpf.c, which is a restricted C program, as we mentioned before. So let's deep dive into the code. We have a function here that is called hello XDP, and it takes a parameter that is XDP context. And this context have the actual network data in it. So the parameter of the data variable contains our each network packet. So we need to parse them into the TCP/IP stacking sequence. For example, firstly, we need to parse the Ethernet header here, and then we will parse the IP header and get some useful stuff in IP header, and we will check the protocol, which is that. For example, IP proto TCP is here. If there's a TCP packet, the condition will work. And we will parse the TCP header here. And here is the logic, the prevention logic here. So we get the source port and destination port from the TCP header, and we will check the header. If there is a fin scan, this is a Nmap, this is a technique that can be done via attackers on our hosts, which is only fin flag is set as 1, and the other flags is remain 0. So this function basically does that and returns as a 1 if this is true, and 0 it is false. So if this is an Nmap scan, so we will drop the packet via XDP drop directive. Or everything is fine, the packet will be passed through the kernel via XDP pass directive. Okay, if the value is triggered, so if the function is triggered, we will add the source IP. This is the attacker, and we will set the attacker to our BPF map, which is can be defined here. It's the hash map that is that names the attackers. The key value is integer and the value is integer. So we will store the IPs as an integer here, and we will count how many packets drop from this IP. So we will increase the dropped packet count from our BPF map. And all the stuff is okay for our kernel program. And let's go to our Go site, and let's see our Go code. Okay, we have some useful functions here. So, for example, usage or integer to IP translation function, as we discussed before. And there is some error handling function, and the logic starts from here. First of all, we read the actual C code. This is the kernel code, which is running in the kernel in the XDP virtual machine. We will read this code via OS read file. And then we will use a BPF module, which is our IOVisor's Go BPF. We will use it, this library today. Okay, we will create a new module via new module function from this source code. And then the module object is created. So we have a function inside our kernel program, which is called hello_xdp. We will load the function called hello_xdp as a BPF prototype XDP. And then we get the function here. So we will attach the function for a network device to trigger each incoming or outgoing packet is triggered. So we will set the device from the OS arguments, and the attach XDP function attaches this function to the given network device, and this function triggered when the packet goes through this interface. Okay, all the stuff is here, and we have a BPF map as we discussed before here. This is called attackers, which is a hash map. The key is integer and value is integer. So we need to implement here in Go side. So we have to create a new object that is called attackers with bpf.newTable function. We will pass the attackers the same name from the C code, and our BPF map can be accessed via this variable. And when we start the program, it waits the Control-C as Burak program command. If the program killed, the contents of our BPF map will be printed onto the screen. Let's look at how it's work in real life. Let's start our Nmap Scan from our host to our victim VM. We will start a Nmap Scan. And you can see that there are two ports are open. The 2020 and 80 is open. And Nmap can determine which is open. And we will start our Go program here, which protects from us from the Nmap scans, Nmap fin scans especially. We can run our main Go program with our interface name, as we said before here. So first we get the interface name from ifconfig. This is emp03s3. So sudo go run main.go and the interface name. Let's start our program. The eBPF programs needs to sudo privileges before start. So our program is running and it started to protect from the Nmap fin scans us. Let's start the Nmap scan again. So there is no output here because all the packets that is sent from Nmap is dropped by our eBPF program. When we kill our protector program, our eBPF program, you can see that the more than 1,000 packets is dropped from this host. As you can see here, we will implement a security application, which is a very, very, very tiny, but it may be useful. So all the things that I've said is today okay. And if you have any question, we can I can answer your questions now.